All right, so there's our given. That's what our goal. Make our tree. So we've got our statement, justifications. The diagram is our given. But from the diagram, do I know anything? So?
I don't know, but 3x minus 9
3x minus 9
2x
plus 2x
equals 4x minus 4.
How do you figure that? What lets you say that these guys add together equals that?
Because 2x is that part, and then 3x is minus 9 is that part, and then 4x minus 4 is the whole thing.
So you're kind of telling me that NM plus MO is going to equal the whole thing.
Yeah.
All right, what rule, though, says I can take two parts of a segment and it equals the whole segment added up? You're not going to use the laws as justifications. Segment addition postulate. Ciao. Segment addition postulates. Now, once I've said that, now I can go ahead and write out what you were describing of saying 2x plus 3x minus 9 is going to equal 4x minus 4. I said the parts add up to the whole. Now I'm going to go ahead and put in the algebraic parts of it. I need to get this rule, though. What rule says I can do that? Or rather, what rule says I can replace NO with this thing up here that I said NO equals?
Substitution.
There we go, substitution. And now it's just algebra, isn't it? Let's see. First, let me clean it up a little bit. I'll combine my like terms. So 5x minus 9 equals 4x minus 4. We'll call that combine like terms. Now what? Subtract the 4? I guess I should do that, yeah. Subtract 4x from both sides. So negative 4. Watch your signs. A lot of students will lose that negative coming down here. That's x minus 9 now. The other thing I'll mention is this combination up here. I've seen a lot of students write minus 3x and have a negative x. Or this stuff that I have in red only happens if you're splitting the sides of the equal sign. So this is actually a nice chance to practice some of these algebra skills that might be a wee bit rusty. And I'll go ahead and add 9 to both sides. Oh, whoops. I forgot to do that. What is that justification? Subtraction property of equality. And that now leaves me x equal to 5. And then what rule? Addition property. Now, with the algebraic proofs, and actually with proofs in general, there are kind of two ways you can do it. There's the stagger step and the two races. The stagger step is how I've been modeling it. Write a statement, write a justification. Write a statement, write a justification. Write a statement, write a justification. And you stagger your way down. Another approach is to just go straight down all of the statements. Follow your thought process. Plan your flight. I can go here to here to here to here to here. Then go back and say, okay, now how did I do that again? Oh, that's right. I use that rule. I use that rule. I use that rule. I use that rule. And fill in the justification second. Both ways of approaching this are good. Part of what I get into trouble is I tend to focus on this back and forth because it's how I do it best, the way I think. For a lot of students, it's easier once you just let your mind go and just keep going with the next thing you can think of and then worry about how to justify it later. You know, as long as you know that each step's valid, because something up there tells you what should be, you can usually go back and figure out that something at a later date. Questions on this guy? All right. So we've got the x equals 5. Now we can go ahead and say, all right, let's, we have to get that. Well, we know that NO is equal to 4x minus 4. How do we know that? It's in the diagram. And that's a given, isn't it? And now I can replace x with 5. What rule says I can do that again? Substitution. Now that leaves me 20 minus 4, which is simply 16. And that's what I set out to prove.
Why did you write that?
Because I can never spell arithmetic appropriately, and since I'm taping this for your parents to watch, I wanted to make sure I didn't look stupid. Which I may have just...
Yeah.
Oh, well. Coffee's still kicking in. And the part of the sales pitch I have with the QED is you can then look and say, all right, is this really what I set out to prove? And yeah, that does match with our initial objective. And therefore, I can say this problem is finished.
Oh,